Introduction to Cryptography and Cryptocurrencies. All currencies need some way to control supply and enforce various security properties to prevent cheating. In fiat currencies, banks and other government-licensed organizations are in charge of the money supply and are constantly adding anti-counterfeiting features to physical currency. These security features raise the bar for an attacker, but they don't make money impossible to counterfeit. The rules of the system. Cryptocurrencies, too, must have security measures that prevent people from tampering with the state of the system and from equivocating, that is, making mutually inconsistent statements to different people. If Alice convinces Bob that she paid him a digital coin, for example, she should not be able to convince Carol that she paid her that same coin. But unlike fiat currencies, the security rules of cryptocurrencies need to be enforced purely technologically and without relying on a central authority. Cryptocurrencies make heavy use of cryptography, which provides a secure way to encode rules of a cryptocurrency system in the system itself. Nowadays, we can use it to prevent tampering and fraud-related incidents from happening. In a mathematical protocol, the rules for creation of new units of the currency. Thus, before we can properly understand cryptocurrencies, we need to delve into the cryptographic foundations that they rely on. Cryptography is a deep academic research field using many advanced mathematical techniques that are notoriously subtle and complicated. Fortunately, Bitcoin relies on only a handful of relatively simple and well-known cryptographic constructions. In this chapter, we specifically study cryptographic hashes and digital signatures, two primitives that prove to be useful for building cryptocurrencies. Later chapters introduce more complicated cryptographic schemes, such as zero. Cryptographic hash functions. The first cryptographic primitive that we need to understand is a cryptographic hash function. A hash function is a mathematical function with the following three properties. Asterisk number on, its input can be any string of any size. Asterisk number 2, it produces a fixed-sized output. For the purpose of making the discussion in this chapter concrete, we will assume a 256-bit output size. However, our discussion holds true for any output size as long as it is sufficiently large. Asterisk number 3, it is efficiently computable. Given an input string, you can determine the output of the hash function in a reasonable amount of time. More technically, computing the hash of an n-bit string should have a running time that is own. These properties define a general hash function, one that could be used to build a data structure, such as a hash table. We're going to focus exclusively on cryptographic hash functions. For a hash function to be cryptographically secure, we require that it has the following three additional properties. 1. Collision resistance, 2. Hiding, and 3. Puzzle friendliness. We'll look more closely at each of these properties to gain an understanding of why it's useful to have a function that satisfies them. The reader who has studied cryptography should be aware that the treatment of hash functions in this book is a bit different from that in a standard cryptography textbook. The puzzle friendliness property, in particular, is not a general requirement for cryptographic hash functions. Property 1. Collision resistance. The first property that we need from a cryptographic hash function is that it is collision resistant. A collision occurs when two distinct inputs produce the same output. A hash function asterisk is collision resistant if nobody can find a collision. Figure 1.1. Formally, collision resistance. A hash function h is said to be collision resistant if it is infeasible to find two values, x and I, such that xi, yet hx, equals a. Notice that we said nobody can find a collision, but we did not say that no collisions exist. Actually, collisions exist for any hash function, and we can prove this by a simple counting argument. The input space to the hash function contains all strings of all lengths, yet the output space contains only strings of a specific fixed length. Because the input space is larger than the output space, indeed, the input space is infinite, while the output space is finite. There must be input strings that map to the same output string. In fact, there will be some outputs to which an infinite number of possible inputs will map. Figure 1.2. Figure 1.1. A hash collision. X and I are distinct values, yet when input into hash function h, they produce the same output. Now, to make things even worse, we said that it has to be impossible to find a collision. Yet there are methods that are guaranteed to find a collision. Consider the following simple method for finding a collision for a hash function with a 256-bit output size. Pick two 256 plus 1 distinct values, compute the hashes of each of them, and check whether any two outputs are equal. Since we picked more inputs than possible outputs, some pair of them must collide when you apply the hash function. The method above is guaranteed to find a collision. But if we pick random inputs and compute the hash values, we'll find a collision with high probability long before examining two 256 plus 1 inputs. Thank you for watching. See you in the next lesson.